we did problems like this on the last worksheet, but those problems were on regular waves rather than standing waves. So I want to make sure, first of all, that when you do this, we're not going to have any standing waves on the quiz. So if it makes it easier for you, you can just look at the standing wave as a normal transverse wave like this. Because a lot of you know how to find the wavelength of a transverse wave. Okay? So they give you the length from start to finish. And they give you an image of the wave, and they give you an amplitude. If you're trying to find the wavelength, rank the wavelength, the amplitude is not an important piece of information. So really, I want you to see what you're given, analyze the wave that is drawn there to figure out what the wavelength is. Okay? And then down here at the bottom is a problem-solving problem. You're going to have not just a problem-solving problem on the quiz, but some conceptual stuff too. So work on warm-up 6-8, and then go back to your warm-up 6-5 and look over it really quickly so that you make sure you understand the concept. So first of all, I'm not just going to go over the warm-up, but I'm also going to highlight key important concepts that you need to know for the quiz. So first of all, you want to keep in mind that when you're trying to find the wavelength, you need to find the number of waves. And so what Jack did here was he took each loop and he found, what was it? He took each loop So each loop actually is considered one half of a wave. So you need two loops in the standing wave, one full up, down, back to center to get one wave. So here you've got 1, 2, and then at this equilibrium you only have one loop, so that's 2.5 waves. So if you take your 25 divided by 2.5, you get your value of 10. I think.
That's broken.
Oh, I see. So the way Jack did it, it's the same process and he got the same answer, but he took each individual loop knowing it was half of a wave, and he divided it by the number of loops, but multiplied it by 2 to make sure that the 2 loops equaled one wave was taken into consideration. So I'm just going to write down the method, length divided by number of waves. So then for here, we get 10. For B, you have 1 wave, 2 waves, and 3.5 waves. So 28 divided by 3.5 gives you 8. Here you've got 1, 2 waves, 20 divided by 2 is 10. And then same here, this is 1 and a half. So 30 divided by 1.5 to get 20. Does that make sense? Okay, so then we've got this ranking of D having the greatest wavelength, A and C being equal, and then B having the shortest wavelength. Any questions about the ranking? Okay. All right, so in this next problem, I like to write out my givens. I've got a velocity of 60 meters per second, and I have a wavelength from the previous problem. The wavelength of wave D is 20 centimeters. I'm solving for frequency, and I have a good equation to do that. Velocity equals lambda times frequency. The problem is I've got a velocity in meters and I've got a wavelength in centimeters. So it doesn't matter which one you switch. I always like to go back to my my regular physics unit for length, which is meters. So I'm going to convert the centimeters to 0.2 meters. But if you converted the 60 meters per second to 6,000 centimeters per second, you would get the same answer for frequency. So I am going to plug in my velocity of 60 meters per second is equal to 0.2 meters for wavelength, and then the frequency is what I'm solving for. You have to remember what lambda represents. It represents wavelength. If I divide the 0.2 meters from both sides, I end up with a frequency of 300 hertz. Another unit that you have to memorize. For frequency, we use the unit hertz. So that gives me my frequency. If for some reason they asked you for the time, it'd be easy to calculate the time because frequency equals 1 over period. And so you can calculate the time by just plugging in your 300 hertz is equal to 1 over period, and therefore period equals 1 over 300 hertz, or 1 over frequency. So whatever value you get for that, if they asked you for a time value. So these are the equations that you're going to want to use for the quiz. You've got the frequency equation, or you can convert it to the period equation. You've got the wave speed equation, and another equation that I want to include, which is not part of the wave equation, the wave equations in your physics helper, but it's in kinematics, is that speed is equal to distance over time. And you are welcome to use that in this unit as well. Okay, let's go into some concepts. Concepts are looking at a transverse wave. So we've got a transverse wave here. Are you comfortable calculating identifying what the crest, the trough, the amplitude, and the equilibrium are? Any questions on that I need to go over?
The crest is the top.
Crest is the top. Yep, this is the crest. This is the trough. And then the amplitude is not from top to bottom, but it's from equilibrium to the top or equilibrium to the bottom. And then measuring the wavelength, you want to make sure that you can measure it all different ways. If I have a transverse wave, I go crest to crest or trough to trough. If you have a standing wave where it has waves interacting with each other, it's not the same method, okay? With nodes and antinodes, you have to use a different method. If you have it from equilibrium, again, start at equilibrium, up, down, and back. Now, here's where it gets a little tricky. If I have a rarefaction, and you have to make sure that you draw these clearly. I had some students draw a longitudinal wave like this, and I can't identify a compression from a rarefaction in this type of wave. So I want to make sure that you do it very clearly. Your compression and your rarefaction are obviously spread out and obviously compressed together. So let me just finish drawing this. Compression, rarefaction. Question? If you have a transverse wave and it has... Yeah, so you do want to be able to identify. You didn't see any compressions in there at all? It might have been a transverse wave where you're supposed to identify crest, trough, rarefaction, and compression, and you wouldn't have any refractions or compressions in a transverse wave. Really? I have to look at it to answer your question. Okay, so you want to make sure when you have sort of these compressions, it's obvious, right? These are compressions, and rarefactions are the opposite, where they're spread out. But how do you find a wavelength out of this? It's easy because we've been doing a lot of standing wave wavelengths. But how do you find the wavelength of a longitudinal wave? Any thoughts? There's a lot of ways to do it, just like there's a lot of ways to do it for transverse. Thomas. You want to go from compression, and usually you start at the same spot. So let's say go from the beginning of a compression to the beginning of the next compression. Or you can do the beginning of a rarefaction to the beginning of the next rarefaction. Or if it's like your concept builder where they had a grid and the grid fell right in the middle of a compression, then you can go to the next center of the next compression. So as long as you have one full cycle, meaning wherever you start is wherever you end in the very next cycle or the very next part of your wave, you've got a wavelength.